we'll get started. We are going to be seeing more about impedance in transmission lines. That's the place where we had last stopped. Right? Just to refresh our memory, the load reflection coefficient, okay, gamma suffix L, okay, was equal to ZL minus Z naught divided by ZL plus Z naught. Okay. Now, we already know that the reflection coefficient is going to be a complex number. It is going to have a real part and an imaginary part. Alternately, you can say that it has a magnitude and a phase. We have seen this from the simulations already. Okay. Now, we are going to touch some aspects on this particular reflection coefficient over here and try to understand the relationship between gamma and Z more closely. Okay. Now, since this is a ratio of ZL minus Z naught to ZL plus Z naught, the first question that we have to put to rest is whether the absolute values matter. Okay. Now, one could always divide the numerator and the denominator by Z naught. Okay. So, that would give me ZL by Z naught minus 1 divided by ZL divided by Z naught plus 1. Okay. So, it seems like the reflection coefficient depends on the ratio of the load impedance to the characteristic impedance, and it does not depend particularly on the absolute values. It is the ratio that matters. Okay. So, an example could be your load impedance, okay, say your load impedance is 50 ohms, characteristic impedance is 25 ohms. Okay. ZL divided by Z naught is 2. So, gamma becomes 2 minus 1 divided by 2 plus 1, that is 1/3. If you take another absolute value, say ZL is 100 ohms and the characteristic impedance is 50 ohms, I have taken the initial values and doubled the value of load impedance and the characteristic impedance, the gamma still is 2 minus 1 divided by 2 plus 1, that is equal to 1/3. So, clear that the absolute values of the impedance does not matter. What matters is the load impedance to the characteristic impedance ratio. Okay. Now, this ratio we refer to as normalized impedance. Okay. Okay. We can say that ZL by Z naught is the normalized impedance. We will begin with some simple cases to understand what this relationship actually means, and the simple case that we are going to be considering is that the transmission line is lossless. Okay. When the transmission line is lossless, okay, okay, the lossless transmission line will imply that Z naught is real. Okay. It is going to be purely resistive. We are going to begin with this simple case and try to understand the relationship between the reflection coefficient and your load impedance. Okay. Now, the way we are going to represent the normalized impedance is that suppose your ZL is not real, it has a real and an imaginary part. Okay. So, the ratio ZL to Z naught will have both real and imaginary parts. Okay. So, let us say that your ZL be equal to some R plus Jx, okay, where R is the resistive part of your impedance, X is going to be a reactive part of the impedance. Okay. Now, there are two things that first we have to make clear before going further, right. So far we have drawn the circuit equivalent only for passive circuits, and we already know that for passive circuits R cannot be negative, alright. We have in our simulations in the past plugged R to be negative, alright, but that is just to prove a point that gain can occur in your medium. However, in passive circuits R is going to be only positive. Okay. So, let us make that clear over here, right. Oh, I wrote the same thing, saying passive. Okay. However, the X could be positive or negative depending upon whether you have a capacitive reactance or a inductive reactance. Okay. So, for the inductive reactance it is going to be positive, and for the capacitive reactance it is going to be negative. Okay. So, these are the cases which are possible for ZL. Now, once you normalize this with Z0 and Z0 is real, it means that you are going to be having ZL divided by Z0 to be equal to R divided by Z0 plus Jx divided by Z0. Okay. We will denote this ratio to be some small r plus Jx. Okay. Now, this is your normalized load impedance. Okay. So, correspondingly here I will just make it ZL, because the capital ZL and small ZL look identical. I will just put a bar on the top to indicate that it is actually normalized with respect to the characteristic impedance of the transmission line. Okay. So, it is R plus Jx. Okay. Now, you can go back to the expression for the reflection coefficient and substitute for ZL by Z0 minus 1 divided by ZL divided by Z0 plus 1. Okay. ZL divided by Z0 is your normalized load impedance, alright. So, you can substitute that in the numerator and denominator. So, we can go ahead with gamma L. Okay. So, we have just substituted the normalized load impedance in the expression for the reflection coefficient. Okay. This means that gamma itself will be a complex number. Okay. It is going to be having some real part and some imaginary part. We have assumed the lossless transmission line case. So, Z0 is purely real, but we are assuming ZL to be anything, it could be anything, right, which means that in the most general case gamma is going to be having a real part and an imaginary part. You could write this as say A plus JB. Okay. What we are interested in now knowing is how ZL bar influences gamma L. Okay. Specifically, the points that we would like to see now are, if I substitute for a value of ZL bar, I know that there is going to be a corresponding unique value of gamma L, alright, and there is a good chance that I want to keep the resistance fixed and change the reactance of ZL just to see how gamma L changes, or I could keep the reactance fixed, vary the resistances, see how gamma L changes. These are the two things that we would like to understand in this particular lecture. Okay. So, I am going to have ZL bar to be written as R plus Jx, and I would like to understand what happens for fixed values of R with varying reactances and fixed values of X with varying resistances. This is all I want to find out. Okay. And the method in which I am going to be doing is I am going to be fixing the value of R and X, and then I am going to be calculating the value of gamma L. It is going to be having a real and an imaginary part, and I am just going to draw a graph. Okay. The graph is going to be like this. It is going to have a vertical and a horizontal axis. The horizontal axis is going to be the real part of the reflection coefficient at the load in this case, right. It could be done for any location in the transmission line, but we are keeping it simple for the beginning, we are just calculating reflection coefficient at the load, right. So, I am just saying that real part of gamma L, and in our lecture, this is going to be denoted by A. So, you could also say that this is equal to A, and the vertical axis is going to be corresponding to JB, or the imaginary part of gamma L, and I am going to take fixed values of R and X, and I am going to calculate what is the value of gamma L, and I am going to make a plot. That is all I want to do, and any other inferences I will draw once I have completed the plot. Okay. This is the exercise. So, I am going to fire Octave, okay, and I am going to do this using Octave. Okay. Now, I am going to start with a simple program to do that. So, I am going to here what I am just saying is, for R is equal to 0 colon 1 colon 0, that means I have fixed R to be 0. Okay. Later on I would like to add a series of R's, so that is why I am writing the program using a for loop. Normally one could fix the value of R to a 0 to be constant. Okay. I want to understand the effect of X. Okay. So, I have another loop in between, right, which will compute the value of gamma. Let us say that I want to have insanely wide range of X. So, I am going to take going from the normalized, these are the normalized values, mind you, okay, these are divided by Z naught. Okay. So, I am going to go from minus 500, okay, just pick the number, you could pick 50, you could pick 5000. I will show the consequence of using all of them in a second. Right. So, I am going to have the normalized reactance going from minus 500 to 500, but my R value is going to be fixed at 0. Okay. And all I want to do now is the reason I have picked a variable I equal to 1 to 10,001 is because I have minus 500 to 500 in steps of 0.1, all right, that corresponds to 10,001 points, all right, and for every reactance value I would like to calculate gamma L, that is all. Okay. So, I am just going to use the formula that we had. I am going to build a gamma vector, okay, is equal to R let me explain this in a second, all right. So, the formula that we have is ZL bar minus 1 divided by ZL bar plus 1. You could also substitute for ZL bar, you could say that this is R plus Jx minus 1 divided by R plus Jx plus 1. You could just bring the real parts together, imaginary parts together, right. You could write this as R minus 1 plus Jx divided by R plus 1 plus Jx. Okay. So, the formula for calculating the reflection coefficient is R minus 1 plus Jx divided by R plus 1 plus Jx, where J is the square root of minus 1. Okay. So, I will go back to my Octave program, okay, and I will complete this formula for calculating the reflection, the value of voltage reflection coefficient gamma. So, it will be R plus 1 plus. So, the reason why we are putting x of I into j is Octave accepts this for the imaginary part. You have to put the variable name first, multiplied with j, j is square root of minus 1 here, I is the index of x for which you are going to calculate the value of gamma. Okay. This is just a detail. So, now I have my resistance fixed and I am calculating a value of gamma for a variety of reactances, and I want to understand the effect of this on the gamma, and I want to make a plot. So, let me go ahead and make a plot. Okay. I simply want to plot the real part of gamma with imaginary part of gamma, right, as I have described. This is going to be otherwise known as complex gamma plane. Okay. The complex gamma plane, I am just using the real part, I am going to be taking it as the x-axis. Imaginary part is going to be the y-axis, and I am going to place a point corresponding to the calculation. Okay. And I am just going to run this, right. Okay. Now, it looks oval, so I am just going to use a command to just make this a little bit more easy to interpret. Okay. Now, the locus of all the points is a circle. Okay. What this means is the x-axis corresponds to the real part of gamma, y-axis corresponds to the imaginary part of gamma. I am keeping r fixed at 0, I am taking x going from minus 500 to plus 500, and I am trying to plot what the value of gamma would be, and it turns out that it sweeps a circle. Okay. So, what this means is that the center of the circle here that we observe is 0, 0, all right, and on the right hand side I notice that it is having a radius of 1, all right. So, it is a unit circle, and that is it, all right. Now, I would like to draw more of these and try to understand what is exactly going on. Okay. So, for now we know that it is going to be a circle. Now, this circle is known as a constant resistance circle, okay, because you have fixed r to 0, but you have just varied x. Okay. Now, I am going to go ahead and make r go from 0 to 0.5 in steps of 0 to 6 in steps of 0.5, okay, and I want to draw a plot, okay, and I want to figure out what is going on, all right. I will just modify my program a little bit to make it a cleaner graph at the end, because currently it will draw with the same color, all right. I want to draw it with different colors to analyze what is going on. On top of that, I would like to have a legend to tell me which color corresponds to what value of resistance. All right. So, I am just going to add a couple of commands over here. I would like to have a legend, okay, and I would like to have the legend outside the graph. Okay. So, I am specifying a location. So, typically I would like to have the legend on the northeast side of the graph, and I would like it to be outside of the graph. So, it is a lot of parameters, but you will get used to it. So, the legend I am going to place it at a location which is on the northeast side of the graph, that is top right, and I do not want the legend to come inside the plot at all, I want it to be completely outside. So, I am just saying northeast outside, it is just syntax in Octave, and I am using the command hold all. It means that when a plot is drawn, it will retain that plot and then it will draw on top of it. For example, if I draw for r equal to 0, when it draws for r equal to 1, I do not want it to erase the previous plot, I want it to hold it in place and draw on top of that. Okay. So, hold all is just saying that hold all the parameters of the previous plot as it is and then redraw the new plot on top of it. Okay. So, these are the two commands that I am adding to it. So, I will run it now. All right. Now, I am having a series of circles, only thing is my legend is not showing up correctly, all right. I will fix that in a second. Okay. However, I know for a fact that r equal to 0 was a unit circle in the gamma plane, all right. So, I know for a fact that this is r equal to 0, and I can tell you that as r increases, it keeps reducing the radius of the circle, and it also moves the center of the circle towards the right. Okay. So, if you keep increasing your r all the way to infinity, your circle will reduce to a point on the right extreme, all right. So, r equal to infinity will reduce to a point because the center will keep moving to the right side and the radius will shrink abnormally low and it will become a point. Okay. So, r equal to infinity is going to have a point on the right side. Okay. So, just to be safer, I will just correct this plot legend. Okay. So, I will just include a string which I will create for drawing the legend. So, I am just say r equal to in text okay. I need a legend string. This is Octave syntax for legend string. I just want to have r equal to for each and every time it draws, right, and everything else is can be understood later. Okay. Okay. So, now it is abundantly clear, for increasing values of r, the circle is reducing in radius, okay, and it is the center is moving towards the right, and that gives me an indication that at r equal to infinity it is going to be a point on the right side. Okay. I guess now you know where we are heading to. Okay. We are trying to see if we can construct a Smith chart, okay, and we are going to construct it on our own. Right. Now, the relationship between gamma L and the resistance should be clear. Okay. So, if you keep your resistance fixed, no matter what value of x you take, all right, gamma is going to sweep a circle. So, it is going to have a fixed value of the reflection coefficient. The magnitude is going to be fixed. The only thing that is going to be changing is the phase. All right. That means for a given value of r, all right, if you change x, the value of the reflection coefficient, the magnitude is going to change, but I mean magnitude is going to be fixed, but only the phase is going to be changing, because it sweeps a circle in the complex plane. Okay. Now, I would like to do a similar thing for the imaginary part. Right. So, I am going to go back to the program, right, and I am going to keep this a little clean. So, I am going to write another for loop. I am going to say for x going from say minus 2.25 to 2. Okay. So, I want to vary x from minus 2 to 2. I am doing this because resistance we were keeping from 0 to a positive number, because we are considering here only passive circuits. Okay. But I know that x can go from negative to positive. So, I am just taking a value minus 2 to plus 2, and I am going to go in steps of 0.25. Okay. And I want to build a vector for the resistor 0 to 0. Mean 0 in steps of 0.1 all the way up to 1000. Okay. The program structure for this part will be similar to this part, just the values are slightly changed. The values are changed because you will notice that if you change the values, some things will become not clear. I'll explain that in a second, okay, once we complete the program. Right. Okay. So, now I'll have for I equal to 1 colon, so this is about 1000, 10,000 and 1. Okay. Right. So, R going from 0 to 1000, and my I value is going from 1 to 10,001, and I will just calculate the value of gamma. Okay. Gamma of I was R minus 1. So, here now it is R of I minus 1 plus x into j, okay, divided by R of I plus 1 plus x into j. The formula is similar to the case that we had written in the previous loop, just that because I am using variable reactance in the first loop and variable resistance in the second loop, the subscripts or the array indices are coming in different positions, but the form is same. It is r minus 1 plus jx divided by r plus 1 plus jx. Okay. And I want to be able to draw this. So, I am going to be copying the plot commands from here. And I want to be able to plot real part of gamma, imaginary part of gamma with some string. Here the value of x is changing, so I am changing the legend string to reflect that, right. Okay. So I am going to run this program. This is what it looks like, all right. Previously we had the circles which were shrinking in radius and moving to the right for fixed value of resistances with varying values of reactance. So the blue circle outermost corresponds to R equal to 0 with J going from one value to another, okay. Now we are having some additional plots that are coming into the picture, okay. Each of them deals with a different value of reactance, okay. So if you look at the legend, that is going to tell you, for example, x equal to minus 2 is this purple plot and x equal to plus 2 is this orange plot. So you can always see where is this purple plot. So x equal to minus 2 is coming here, all right, and x equal to plus 2 is going to the top, right. So it tells you that x equal to plus 2 is creating something here, x equal to minus 2 is creating something here, all right, and this representation is simply known as a Smith chart. So all you are doing is taking different values of your load impedance that is normalized to the characteristic impedance of your transmission line, and you are plotting the root locus of all these points, and you are plotting the variation of real and the imaginary parts, right, on the complex gamma plane. Okay. Each and every point here is telling you the value of gamma. The gamma is going to be having a real part and an imaginary part. Okay. So this is known as Smith chart, but we have to be very clear about the kind of Smith chart. The kind of Smith chart that we are seeing here is an impedance Smith chart, okay, because we started with ZL by Z0 minus 1 divided by ZL by Z0 plus 1, right. So it is an impedance Smith chart. For a minute, let us look at this impedance Smith chart and try to see try to understand what it actually means, right. So if possible, I will save this graph. As a JPEG. And I will import that over here. Okay, there we go. Okay. Now I will mark a few points on this chart. Okay. So the right hand side corresponds to this point, corresponds to R equal to infinity. It also corresponds to x equal to infinity. Okay. The x equal to minus 2 curve lies over here, I mean x equal to minus 2 is here, x equal to plus 2 is here, alright. As you increase the value of x, it keeps going towards this side, alright. So R equal to infinity, x equal to infinity is the point on the right, alright. Now let us try to figure out what that physically would mean. R equal to infinity, x equal to infinity will mean that you are having an open circuit, all right. So, we mark this region as an open circuit. Now, we will also look at this point. This point is on the complex gamma plane, all right. We can also tell what the value of the reflection coefficient at the load is going to be. The value is going to be equal to 1 because the angle it makes with respect to the real axis is 0, has no phase. So, we can go back to the derivation that we made for the reflection coefficient for an open circuit. We would have got ZL minus Z0 by ZL plus Z0 to be equal to 1, all right. So, the analytical way of finding out the reflection coefficient is by using the formula ZL minus Z0 by ZL plus Z0. The computational way you are already aware, write the telegrapher's equations and try to see what is going back, all right. This is the third method, which is the graphical way, okay. Now, you know that on the right hand side of this chart, R is equal to infinity, X is equal to infinity. So, if somebody tells you that the load impedance is open circuit, you can quickly go to the Smith chart, mark this point and say that the reflection coefficient is going to be 1. Let us go to the leftmost point, okay. The leftmost point, okay, is an interesting point because it is R equal to 0, okay. However, there is a straight line that goes over here. The straight line corresponds to x equal to 0, okay. Because the radius of the circle becomes infinite in that expression, it looks like a straight line, okay. So, R equal to 0 and X equal to 0, we already know what the physical interpretation would be. It is going to be a short circuit on the left hand side. So, the short circuit is represented on the impedance Smith chart on the left hand side of the complex gamma plane. If somebody says that the load resistance is short, okay, you can say that yes, the reflection coefficient is going to be minus 1, okay. You can look at the axis values over here, right, all right. It is going to be minus 1 and the reflection coefficient is going to be minus 1. So, given a load impedance and given a transmission line characteristic impedance, and if the transmission line is lossless and you are given a value for the impedance of the transmission line characteristic impedance, you should be able to go to the Smith chart, quickly identify the point, immediately say what the value of complex reflection coefficient is going to be, okay. Now, there are also two other points that we have to remember, okay. There is a point going upward, all right, this point, right, where your x is positive, okay, where your x is positive, but the resistance is 0. It is a circle which corresponds to R equal to 0 and x is positive. So, that corresponds to pure reactance, right, it is an inductance, okay. And at the bottom you are having pure capacitive load. We know that if your transmission line is going to be having loss, it is going to be lossless, it is having a characteristic impedance in ohms. If you connect an inductor or a capacitor to it, the reflection coefficient magnitude is still going to be equal to 1. Only the phase is going to change, and we already know from our circuits that in pure inductor and pure capacitor, the phase change between the voltage and the current is going to be 90 degrees. Okay. So, if you want to measure the angle, you could go from the horizontal axis and reach any of these points, you will end up getting a 90 degrees, right. But here we have to be a little careful with the interpretation because gamma L is voltage reflection coefficient. It is not the same as the phase between your voltage and current, it is the voltage reflection coefficient. So, it is V minus divided by V plus, okay. So, it means that the reflected voltage is going to be 90 degrees out of phase, all right, with respect to the incident voltage, right, for the top and the bottom points. These are the important points in your Smith chart, okay. Now, given some value of load impedance, okay, and suppose it has a real and an imaginary part, the first step that you will do is normalize the given load impedance with respect to the transmission line characteristic impedance to get small r and small x. You will then try to identify the circle corresponding to small r, okay, and then once you have identified that circle, what you will do is you will identify the circle corresponding to the x, okay, value of x that you have in your from your normalized transmission line load impedance. You will try to see whether it is this way or whether it is that way, and then you will take the intersection of those two circles and make a dot. Say for example, I will make a dot over here. This is going to be your load impedance marked on a Smith's chart. Okay. This is going to be your load impedance marked on the Smith's chart, and what that point tells you is a location of gamma in the complex gamma plane. So, if I want to calculate for an arbitrary load impedance what the reflection coefficient is going to be, I can just take the center of this circle and I could calculate the Euclidean distance from here to there, alright. In other words, I could take the real part, imaginary part, and express gamma to be a real plus j times some imaginary part. I could also do this in the magnitude argument form. I could take the distance and say that this is mod gamma, and I could take the angle from here and say that that is the angle of the reflection coefficient that I am going to be getting. Okay. So, this is how you construct a Smith chart. So, construction of the Smith chart should be clear, right. Now, in many of the cases in transmission lines, one would use actually admittance instead of impedance, because many times you would connect something parallel to your transmission line to achieve what is known as impedance matching, which is where we are headed towards. Many of the times we do not cut the transmission line and insert something in the middle to achieve impedance matching. So, you will have a transmission line and you will connect something in parallel to it. So, when you connect something in parallel, it is easier to deal with admittances. Okay. So, one could also do the same for admittances, but are there going to be any significant differences? Let us have a look at that once again. Okay. So, if I say that my characteristic admittance is y naught, instead of z naught I am having y naught, this is the characteristic okay, and suppose the load admittance is given as YL. Okay. And let us say that we are dealing with a lossless transmission line, which means that Y naught is going to be having only a real part. YL could be anything, could have a real and an imaginary part, and you could write this to be say G plus J Y or something. Previously we had R plus Jx, you could write this as G plus Jy, right. So, you could go back to your reflection coefficient formula, right. So, we had is equal to ZL by Z naught minus 1 divided by ZL by Z naught plus 1, okay, that is what we had. So, we could always write this down as right Y naught by YL by YL by Y naught by YL plus 1. This would be the way to calculate reflection coefficient given the admittances. Okay. Okay. So, now I am having Y naught by YL minus 1 divided by Y naught by YL plus 1, right, and we could also do something else. We could say that Y naught by YL seems a little weird. Okay. We have normalized impedance with respect to transmission line impedance. We would like to do the same thing, all right. We could simply write this down as Y naught minus YL divided by Y naught plus YL, right, and then divided by Y naught and make our life simpler for the normalization process. So, that will look like 1 minus YL by Y naught divided by 1 plus YL by Y naught, okay, and the normalized admittance you can call this as some YL bar Okay. You can go one step further, all right, and say that I can write this down as minus YL bar minus 1 divided by YL bar plus 1. Okay. This will be the form of your load reflection coefficient calculated using load and transmission line characteristic admittances. Okay. So, if these values are given, the way to calculate gamma is going to be minus of YL bar minus 1 divided by YL bar plus 1. Let us write a simple program and try to plot, okay, the different possibilities for gamma for different values of real and imaginary parts of YL. So, just like the previous program, first we are going to take G to be some fixed value, say 0, 1, 2, etc. For G equal to 0, we are going to sweep the Y from going from some negative value to positive value and try to see what is going to happen. Then we will keep Y to be some fixed values and then vary G and draw these curves. Okay. But the formula for calculating gamma will be now this formula that we have created. Okay. So, I will go to the program and I will create a new figure for doing this. All I will do now is I will copy the previous code entirely and I will start replacing things R with G, all right, and I will do some manipulation so that I can get the expression that I have, right. So, I am going to go ahead. Okay. So, this is going to be okay. So, I want to go for G equal to 0 to 0.5 to 6, let us say that, right. I am not going for negative values of G because we are dealing with passive circuits again, okay. And X is going, instead of X I am going to use the variable Y, right, is going to from minus 500 to plus 500, keeping everything else the same, all right. Now, the formula that we had was minus of G minus 1 plus Y of I into J divided by G plus 1 Y of I into J. This is the formula we had written. Okay. So, just to go back and write this in terms of okay, and you could write down the real and the imaginary parts together. So, you will have minus of G minus 1 plus Jy divided by G plus 1 plus Jy. That is the exact formula that I am putting in the program. Okay. This is the value of gamma that is calculated using admittances, okay. And I would like to say that this is for G equal to everything else remains the same, and then I want to make this for the next loop for Y. Y goes from say minus 2 to plus 2, this becomes G. So, R is being replaced with G, X is being replaced with Y, that is all, okay. And then the formula for gamma obviously is different, okay. So, we have gamma formula is minus G of I minus 1 plus Y into J divided by G of I plus 1 plus Y into J. Again, I want to make this X to Y, X to Y. Okay. So, all I have done is copied the program, changed the formula for gamma, used admittances and just changed the variable names to reflect the real and the imaginary part of the admittances, okay. And I am going to have this in a different figure, okay. And to be clear, what we can do is the first figure we can give a title. So, I will just give a title to the first figure. I will just call this as impedance, right. I'm going to call the second one as admittance. I'm going to run the program. Okay. So now I have two graphs. Just take this, restore it a little bit, and auto scale. Put figure 1 and figure 2 side by side. And you should be able to see something that's happening, all right. Both of these are Smith chart because you are just representing impedances or admittances on the complex gamma plane. X axis is going to be your real part of gamma, y axis is going to be the imaginary part of gamma. The purpose of doing this is, suppose you are given a load resistance or a load impedance and a transmission line characteristic impedance or admittance, you should be able to quickly go to the Smith chart, find the intersection of two circles corresponding to that, and then say this is the value of the reflection coefficient. That is the objective. Okay. Now, we can clearly see that if you are going to deal with admittances, there is a different figure that is popping up. Okay. We notice that the right side figure is a mirrored version of the left side figure. Okay. So, the x axis is flipped. Okay. On top of that, if you see in detail, the y axis is also flipped. Okay. The x axis is flipped, the y axis is also flipped. Okay. So, this is going to become confusing for people. That means the interpretation is going to be different. So, if we take this curve, right, and we make a version of this, okay. Now, we have to start marking some points. The left hand side is corresponding to g going from 0 to infinity. Okay. As your g keeps increasing, it will go all the way to the left hand side point. Right. Similarly, you will have to see what is going to happen to the right hand side, all right, and then the interpretation of what is short circuit and what is open circuit will change, right. It will not be the same as your impedance chart, so one has to be a little careful. Okay. But I have never seen somebody use admittance Smith chart like this. Usually when people talk about Smith chart, they usually have a way of orienting the Smith chart before starting any problems. They always do the orientation in this manner, right. That is, as you go to the right, the circles should become smaller and more closely spaced, all right, and your reactance, constant reactance circle should go from the right side branching out. So, it should be flaring out from the right hand side. This is the normal orientation of Smith chart that people use. What they do for admittances is that they flip the axis. Okay. So, instead of having the positive axis, they will mark it the negative axis and simply continue to do the problem. But there are some nuances to that and we will have to see them in detail. But for now, you should know not only how to use the Smith chart. The objective was that you make your own Smith chart so that you get a feeling for what the chart actually is. It is just gamma plane and you are marking different load impedances and load admittances. Okay. So, the first effort is to make your own Smith chart, then only you understand what is going to be happening with respect to your admittances and reactances. Now, what we are going to be doing is we are going to use this to do impedance matching using some different techniques. Okay. So, we will meet in the next class for this.